the basic proton NMR tells us about the the subtle difference in terms of the local environment of protons. So in some cases, like if you recall what you learned in organic 1 cyclohexane derivative, you probably know that all cyclohexane derivatives they're going to be always in one of those chair conformations. Okay? And in a chair conformation, let's say it's just cyclohexane, unsubstituted cyclohexane. There's two kind of protons. One is exoprotons, one is equatorial protons. Their environment actually is slightly different. Okay, so technically, we should be able to see you have two kind of protons in cyclohexane ring. Okay, and but in reality, because NMR is is a relatively slow technique under the conformation change. Okay, and we know cyclohexane always have the two chair conformation, they always flipping between each other very rapidly. Okay, so because of the NMR is relatively slow technique, so the ring flipping process at the room temperature is much faster than basically when you collect one NMR, the ring already flipped multiple times. Okay, during the time you can collect the NMR, the ring already flipped maybe countless times. Okay, so basically that's why the NMR typically cannot capture the difference of those two protons. Instead, what we see is average of those two protons. But if your instrument is equipped with physical means to lower the temperature to, let's say, -80 Celsius degrees, something like that, then you actually, if you're at a lower temperature, ring flipping process becomes much slower. In that case, NMR actually could be able to see distinct axial and equatorial protons. Okay, so this just thing about the conformation. Now, let's do a full-scale practice on how do we decode, the real-world NMR spectrum. Okay, so you're gonna see something similar in the test. So be sure to apply the process. I'm going to show you. Okay, so when you're given a proton NMR, spectrum, first thing is look at how many peaks and find out the area on the individual peak. So the area on the individual peak is showing by those S-shaped curve. So you should measure using a ruler to measure the step height of each of those curves. So here, just for I already showed you how to do that. So I'm not gonna go through the process because we only have limited amount of time here. So I'm just give you the result in terms of the area on each peak. So this is a 5, okay, this is a 3, and this is a 2, this is a 1, and this is a 1, okay. And for this particular problem, we know this is a proton NMR spectrum of one of isomers of the C9H12O. It's alcohol, okay. Tell you it's alcohol. C9H12O. So it's supposed to have 12 carbons. So do we have all the 12 carbons? Oh, let me say 12 protons because C9H12. Okay, 9 carbons, 12 protons, 1 O. Okay. So do we have the 12 protons first? Add the protons together. Do we have the 12? Yes. Okay. So that means the area is correct. Okay. So this is the first thing. Okay. Then we look at the chemical shift values, try to identify what the protons may what kind of protons may be. Okay. So the first thing, look at the very eye-catching one. You have a peak at 7 ppm. Well, this the peak shape is very ugly. So forget about the, as I said, obviously, if you look at the spin splitting of this peak is very, very complicated. Okay. So for the time being, we just treat it as spin splitting pattern. We only, at least at this level, we only extract the information, physical quantum information from those peaks. They have well-defined splitting pattern, like a singlet, doublet, triplet, and multiple tab. Okay? If a peak has very complicated splitting pattern, we don't use it. Okay? Like this kind of very complicated, we don't use those. We only look at the peak area chemical shift value. Okay? So like here, we have 5 protons, chemical shift value around 7 ppm. If you check that chemical shift value table, you're going to have it in your test. Okay? You immediately see this is typically the proton, aromatic proton of benzene. Okay? And the 5 of them, what does that mean? Means this benzene ring is a monosubstitute because of the, if unsubstituted benzene should have 5, it should have 6, right? Unsubstituted benzene should have 6 protons, C6H6. 5 of them means monosubstituted benzene. Okay? So this signal, this is the first thing. Okay, about the fragment identification. So okay, we have monosubstituted benzene. If it's unsubstituted benzene, parent benzene should have 6. Okay, 5 of them is monosubstituted benzene. Okay, so this structure unit. Second one is the 3 protons. Okay, if you have a peak with 3 protons, almost certain. Okay, if or multiple of 3, if it's 3 protons, 6 protons, if 3 protons, almost certain come from methyl group. If 6 protons come from 2 methyl groups. If 9 protons come from 3 methyl groups. Okay, so this one you have at 1 ppm, around 1 ppm, 3. This is come from methyl group. Okay. And the next thing is we know it's alcohol, right? It's alcohol, so we know must be a carbon connect to the OH group. So because it's alcohol, must have a carbon connect CH group. And this proton, I'm talking about this proton, okay? This proton, due to the deshielding effect of the OH group, electron joint, this proton chemical shift usually pretty high, somewhere between 3 and 5. Okay? Usually 3 point something, but depending on the rest of the structure, could be close to 5. Okay? So that proton, where it is, between 3 and 5, only one signal, right? So the CH proton next to the OH, okay, that proton should be this guy. This one, this all you should be able to under this connect to O, okay? Now the other thing is we know the methyl peak, okay? It's a triplet. What does it mean, the triplet? Means the methyl group must connect to a CH2. That's the well-defined spin split information. Always use it, okay? Because methyl peak splitting to 3 lines, so the methyl protons must have CH2 connect to it. Okay, so if this is a methyl, must have CH2 connect to it. And this CH2 must give you this signal because of CH2 must give you a peak of 2 protons, right? So you only have one signal give you 2 protons. And so that the CH2 must give the peak at 1.7 ppm. Now what is only one peak left, not assigned. What's that peak? 2 point something. 2.3 peak, not assigned. So that must be the OH peak because that's only one proton left, right? So this must be the OH. So what we do next is just assemble those things together, okay? So now look at the structure fragment we have. We have one central piece. In the central piece with at least 2 points of connection, okay? And this guy is central piece, okay? One central piece, okay? Rest of them all end piece. End pieces means only one connection. So just try to connect those things with the the central piece. So obviously, if you look at this is the CH, okay, OH, and the one connect to benzene ring, and the other end connect to CH2, CH3, okay. Then you can confirm whether this assignment is correct, okay. So by look at a more complicated spin splitting pattern, okay. So if you look at what call we know this one is 2.3 ppm, and we observe a doublet, okay. So we check how many doublet means only has one vicinal proton, and this OH indeed only has one vicinal proton here, okay. So agree with what we have seen, and these CH2s, okay, well, it should have very complicated splitting patterns because it has 3 vicinal protons here, okay, and 1 vicinal protons here. Yes, very complicated. 2 kind of vicinal protons. The splitting patterns will be very complicated, okay. So yeah, so it confirms for the analysis confirm the assignment, okay. And the other thing, okay, if you want to see this CH proton, okay, is supposed to give you the 4.5 ppm, the peak. So why the typical CH connect to O is 3 point something ppm. Why this chemical shift value is so high is because look at this proton. Not only is the proton direct connect to oxygen, also is a benzylic proton. So the benzylic proton also make the chemical shift value a bit higher than usual. That's why you have the 4.5 ppm. And you actually can further check its splitting pattern. You see this one, the signal 4.5 ppm is a triplet of doublet or doublet of triplet. So basically, this proton is split by the OH proton into doublet, okay? And every doublet is split by triplet by those 2 CH protons. So yes, this just further confirms the assignment, okay? Then next one, again, write down the peak areas. This is a 5, and the list looks like 3 and 2, 1, 1. Still is C9H12O, okay? So the peak areas, right? Okay. So again, this one's a methyl, so this is gonna be CH3. Okay. And this one, 5 aromatic protons. Forget about the complicated shape, okay? So 5 aromatic protons, so it's monosubstitute benzene, okay? And then the next thing is this one, okay? Again, this proton close to 3 something ppm. So this single proton again is connect to O. And then the this guy, the 1 point something, this guy, what proton it is? Can you guess? This one? Look at it. We have, we assign this one to CH to O. Okay. So what this single proton can be? Huh? Do you think it? Yes, OH. Yeah, very good. Because that's only single proton left. Okay. OH, So this one has to be OH. And so what is this? This then it should be 2 of them. It has to be CH2s. Okay. Now the thing is here, we have 2 central pieces. The CH, those are end pieces. Let me color. So let me put in red. So this is end piece. OH group obviously is end piece. The CH3 also end piece. Okay. So you have 2 central pieces. So we need to do the further assembling before we get to the compound. So obviously the OH group, the has to go here because they don't have other option because it's alcohol. So OH group has to go here. Okay. So now we have to think, how do we connect methyl group? So in this case, we have to look into make the use of spin pair of the methyl group. See, the methyl group is what? Is a doublet. Okay. So doublet means the methyl group must only have 1 vicinal proton. So the methyl group obviously cannot connect to CH2. If methyl group connects to CH2, would it be triplet, right? So the methyl group must assemble to a carbon only has 1 hydrogen only. So which the piece methyl group must be connected to? So obviously, methyl group cannot directly connect to aromatic ring because that seals the compound, right? Where the methyl group connect to? Methyl group connect to here or here. It cannot connect CH2. Connect CH2, it will give you triplet, right? The methyl group only can connect to here because this one only has 1 proton. So now we assemble based on the the multiplicity. We know methyl group must connect to here. Okay. Because connect here, you can have the doublet you wanted. Okay. Now basically we have we already combined the CH3 and OH with this piece. So now we have the we can eliminate those pieces. So we have 2 end pieces plus 1 central piece. So we just put the CH2 become only central piece, okay? And the 2 end pieces combine with the CH2s. So we get this compound. This is a 1 end piece, and CH2 is the central piece. Okay, then connect to the CH, OH, CH3. So that is the compound. Okay. You can confirm that this is gonna be the right compound. Okay. See why the CH2, the chemical shift value is a bit large, 2 point something, because it's a benzylic proton. CH2 is a benzylic proton. Also, on the indirect impact of OH group. So the CH2's chemical shift value is a bit high, close to 3. And if you look at splitting pattern, is also somewhat complicated because it's those two protons, they could, because see here this is a chirality center, okay? Here is a chirality center now. This carbon is a chirality center. So those two protons, they are diastopic protons. Okay? So they will split each other, and the both will be split by this. Okay, so that's why you see this complicated splitting pattern. Okay? Anyway, and then let's look at the third example. Again, it's C9H12O, isomer. C9H12O isomer. Okay. So if you look at the area, still 5. Do we have 3? Yes. And the 2, 1, 1. Okay. So again, the 5, 1 is the monosubstitute benzene ring. 3 is CH3, and this 3.6 ppm. This one is the CH2 connect to the O. And then the look at the splitting pattern. It appears, let's say it's a doublet. Okay, it appears doublet. So this one is supposedly connect to only the one other only have one vicinal proton. But let's look at the later. But now we identified the 3 kind of protons. So you only have these 2 protons not assigned. Okay. So in this case, we should make use of the spin splitting pattern of that methyl group. So what you see here is well-defined doublet. So this methyl group must be bound to what? CH. Okay? So you basically have the under that proton, okay? If you look at this proton, okay? It must at least split into 4 lines, because this proton have the 3 methyl protons as a vicinal proton, right? Must at least 4 lines, okay? So which signal that proton? It's 2.9 ppm or the 1.8 ppm. Which one? You think it's this proton give you this blue peak or this black peak? So this proton give you this peak or this peak? Which peak? I think either blue peak or black peak. So this proton gives you blue peak or black peak. Blue peak is here, black peak is singular. The blue peak, because we know at least 4 lines, right? So this one should go here. Okay? So the OH. So this is this guy. This one obviously is OH. So now once OH identified, we can put together with this one. Okay. So now we have how many pieces now? So this is a one end piece, this second end piece, and this is a central piece. Just put them together. So I would suggest you go through the after class, go through the same process of doing again. So, only by after doing it, you can learn. Okay, learn it well at least. Okay, so then you put this central piece with the end pieces. So CH3, CH, then or you can confirm that indeed that is the correct structure. Okay. The last thing again, here is a 5 proton, here is 6 proton. This look at 1 proton. This is pretty straightforward. 5 proton around 7 ppm. Again, monosubstitute benzene. Okay, and the 6 protons, 2 CH3s. And then only one, that's the OH proton, because that's only 1 proton left. Okay, so then what you have, everything seems end pieces. Monosubstitute benzene, CH3s, OH, all end pieces, right? All of them end pieces. So what is missing? How many carbons we have here already? It's C9H12O. C9H12O. Okay. So the basic we have 6 carbon here, 2 carbons here, 8 carbon. 1 carbon missing, right? We have all the protons, 12 protons, oxygen. We all have there. Okay. Just 1 carbon missing. So that's carbon, missing carbon. There's no protons only. Because we have 4 end pieces, right? So we need a central piece with no proton on it. Okay? That's why I don't see it in proton number. So that is the hidden central piece. So the carbon, okay, then connect the OH group, methyl group, methyl group. Just because of on this carbon, there's no proton, so you cannot directly see it on the proton NMR. So this one, okay, because you don't have protons on it, so you don't directly see it on proton NMR. Yes? No, I only watch the recorded video. See the process, you see the point here. Because only join this doesn't help. You have to go through the process. That's why I purposely don't put on it. I want to show you the process. If I just put on it, it's not really useful. Yeah. That's why I going through the process. Leave the plan, going through the process. If you want to watch the recording. All right, so that's basically this here concludes the proton NMR, and this is the most important spectroscopic technique in this chapter, and it's the most important spectroscopic technique for the chemists. Okay, then the next one we're going to talk about something also important but not as important. Is called carbon-13 NMR spectroscopy. So it's basically the inorganic compound we're dealing with carbon-based compound. You have a lot of chance in protons. That's why proton NMR it's easy to collect. And the proton, each proton gives you about 100 times more intensity than 1 carbon-13. And for whatever reason, I don't want to explain in great detail because it's not too much direct result organic chemistry. It's very, very difficult to study carbon-12 NMR. Okay? It's not carbon 12 is the major isotope in carbon. It's actually very difficult to study carbon 12 in the spectrum. So chemists just found that carbon 13 NMR spectrum actually very simple, easy to understand. So that's why chemists opt to study carbon 13 in addition to the proton. So the why we want to study carbon 13 because there's carbon 13 is a clear advantage. Okay? So the carbon 13 still after all reflects the environment of the nuclei, but only one thing look at the carbon, the other look at the hydrogen. Okay? Because hydrogen usually connect to the carbon, so hydrogen is indirectly reflect carbon. If you look at carbon 13, then it will directly the reflect the carbon. So but the biggest difference between proton and NMR is that the carbon 13 the signal is about 10,000 times weaker than the proton. Okay? So that basically makes a lot more challenge to collect a high quality carbon 13 NMR, the spectrum. So basically carbon 13 NMR problem is very, very low sensitivity. As I have told you, typically you only need about 1 milligram to collect a high quality proton NMR. 1 milligram. But you need probably like 30 to 50 milligrams to collect a high quality carbon 13 NMR. And typically you need to spend a lot of longer time on the instrument. And typically if you use the instrument, you have to pay for it. So it's more costly to collect carbon 13 NMR. So carbon 13 NMR is of much lower sensitivity than proton NMR. But obviously this is an advantage, but otherwise chemists won't be doing carbon 13 NMR. The biggest advantage is the carbon 13 signals are spread over much wider range than the proton signal, making it easier to identify and count individual carbons. So in other words, we can say carbon 13 NMR has much higher resolution than proton NMR, about 3 times higher resolution. So just give you an example. Here is a proton NMR of 1-chloropentane. So technically you have 1, 2, 3, 4, 5 types of chemically non-equivalent the protons. Okay? But obviously here you only can resolve 4 peaks. Okay? So we know that this guy is here. Okay? I hope you all know. Because of the chlorine is a powerful electron withdrawing group. So you all know this peak come from those 2 protons, and the methyl one come from these 3 protons, obviously. Okay. So this one come from here, and these 2 protons give you this peak. And the problem is those 2 CH2 protons, okay? Those 4 CH2 protons, okay? They are actually, technically, these 2 protons should have a bit higher chemical shift value than those 2 protons. But their difference is so small so that the signals from those 4 protons, they actually give you a single broad peak. You cannot really resolve all of them, okay? Now, look, if you look at the carbon 13 NMR, then you can clearly identify 5 carbons. So you have 4 carbon 13 NMR from carbons. We don't care about the protons. So you can see you can apply the same way as we learned from proton NMR. So carbon 13, again, they are measured using a relative unit for chemical shift. Has nothing to do with the instrument, only relate to the local environment. Nothing to do, just like protons. And if you look at still immediately low, carbon 13 NMR chemical shift value can go about 200 ppm. And typically for a proton NMR spectrum, 0 to 10. Here, 0 to 200. So resolution immediately see about 20 times higher. Okay? And then here, you can actually count individual carbons. This carbon give you this peak, this carbon give you this peak, and this carbon give you this peak, and this carbon give you this peak, and this carbon give you this peak. So you can directly see the subtle difference because of the the different distance to the inductive reaction withdrawing chlorine atoms. So you can see all different carbons. Okay. So strongest impact has a higher chemical shift value. The highest chemical shift value. Then move forward, to the left. Once further away, you're gonna see smaller chemical shift value. Under the chemical shift value, again, is pretty much the same as the protons. If you see we have seen this in case of proton chemical shift value difference because of the electron withdrawing different electron withdrawing group with different electron withdrawing power. You see fluorine for the methyl protons 4.3, 3.4, 2.5, 0.2. Okay. Similarly, the carbon on those the compounds, they have the similar trend. So if a carbon electron density is lower because of mostly electron withdrawing fluorine atom, stealing electron density away from it, so the chemical shift value is highest. Okay, so exactly same trend. Only thing is you see that in case of a proton chemical shift value, you see a spread of 4.1 ppm from methane to fluoromethane. But here, from methane to fluoromethane, you see a 77 ppm spread. The resolution is about the spread is about 20 times greater. And similarly, you will see the same argument. In case of the protons, we know the CH4 protons have a lower chemical shift value than CH3 protons. CH3 protons have lower chemical shift than CH2 protons, which have lower chemical shift value than CH protons. Now, similarly, if you look at carbon, if a carbon connect to 4 hydrogens, lowest chemical shift value. If carbon connect to 4 carbons, highest chemical shift value. Same argument, because after all, carbon is slightly more electronegative than hydrogen. So each attachment of a hydrogen atom to the carbon will increase the electron density on the carbon a little bit. That's why the methane has 4 hydrogen attached to it, and the highest electron density, lowest chemical shift value. And here, this carbon, I'm talking about this carbon, okay, has 4 carbon attached to it. It's a quaternary carbon, so no hydrogen donated electron density to it. So this carbon has the highest chemical shift value. Same argument, okay? And almost same argument as we have seen in case of the proton and the Ma. The sp2 hybridized carbon has a higher chemical shift value than sp, and I'm sorry, sp2 hybridized carbon has a higher chemical shift value than sp3 hybridized carbon, and but sp hybridized carbon has a lower chemical shift value than sp2 hybridized carbon because the circulation of pi electrons. Okay, that is exactly the same trend as we learned from proton and Ma. So chemical shift value all the same. Okay, so the quiz should come up at 9:50. Okay. And but the one thing is quite different from the proton and Ma is the peak intensity of carbon-13 in carbon-13 and Ma. Doesn't make any, it carries no meaning. So peak intensity in carbon-13 and Ma has no meaning. No meaning. That's completely different from proton and Ma. So in carbon-13 and Ma, it only tells you about the types of carbons and the chemical shift values. no peak area, no spin splitting. Okay? That's related to how carbon 13 NMR signal is collected, but no intensity information, no spin splitting information. Carbon 13 NMR signal always single line. Okay?